Hello, I want to welcome all of you on our next webinar from the DigiFoF. Our topic today will be computer vision for manufacturing industry application, and we'll be working on a case study of textile industry. My name is Zbigniew Misiak, I'm your host, but our presenter will be Remus Brad. Here you can see some technical aspects that will help you for the session. We are using GoToMeeting, GoToWebinar software, so all microphones are by default muted. If you have any questions, please type them into the chat window so that we can answer them at the very end of the session. This will be a very interesting session, I know, because we had the discussion even before it began, so I think you will have lots of things to ask about. So this is for a technical aspect, so during the session feel free to ask questions and I'll pass them afterwards to Remus. And our presenter today will be Remus Brad from University of Sibiu. Here you can see his research interests. So he is a IE senior member, and he currently focuses on image processing, motion estimation, and medical imaging. And here you can see about his career. And now, without further ado, I would like to give floor to Remus. Floor is yours, and please continue with the presentation. I'm passing the presenter to you.
Okay, hello everybody. Thanks for joining our webinar today. So I will start with the agenda that we will have today, the motivation of the automation in the textile industry, and because this is the case study that I will make today, due also to my experience in the field. I have published many papers and done many research in the field. So after the motivation, I will talk about some aspects of image processing in the detection of defects in the textile field. I will give an overview of some techniques that can be used in order to detect the texture, and of course the portions where the texture is not present. In this case, we will consider them the defects. Because it will be, let's say, a practical webinar, I will show you how we have implemented this kind of system in a research contract that we have done at the university with a multinational Takata Petri, former Takata Petri, now it's called Joyson, firm that is producing airbags for cars all over the world. And in this respect, I will also point it out another research done also in the view not of detecting the defects in the textile, but also detecting the sewing defects also in the case of the airbags. And at the end, I will wrap up everything with some conclusions regarding the control stages, and we will finish with the questions. Okay, the motivation generally is due to the fact that as you can find it out in other studies made and published in the field, the textile industry is the one with the lowest automation. This is also the reason why the production sites are always in countries where population has a low income, and there is required a lot of manual work in producing the goods. Also, the quality requested for the goods is very high. The quality cannot be achieved only by making an intensive inspection process, and this is why the need for automation in the field is higher and higher. I will also point out the fact that this kind of inspection, because it's done manually by humans, is based actually on vision, and computer vision can be, and it is actually in this moment used in the field due to the fact that it's very robust, it's flexible, it's not affected by the limitation of human beings. It doesn't suffer, for instance, of fatigue or other causes that, like the weather, for instance, or illumination, that can be distracted, and automated inspection can help in finding defects of the textile and ready-made goods. So I will give you, let's say, an overview of how the defects in textile it's done. Actually, automatic production it's quite impossible just in the moment for the textile goods. I'm talking here not tech goods that are very simple to produce, let's say, like nowadays the mask that we will need to wear, but I'm talking about shirts or trousers or things that are more complex to be produced. So in order to provide the client with a high level of quality, inspection is required. Inspection is required, but not at the end, because you can ruin the product if you are doing the inspection at the end. You need to have some stages of production, and of course the need for automation it's very important. So I will try to point out two aspects of control. One is based on texture on the fabric, and the other one it's based on the in the process of assembly of the textile goods by sewing. So both of them will have a case study on the airbags production, because as I told you at the beginning, we had some contracts, research contracts with the well-known industry in the field here in Sibiu. So what is texture? Because actually what we will need to detect is something called texture. Texture is based on the unity of a single composition of pixels, because we are talking about images here, which is called the texton. And this unitary composition of pixels is then replicated actually in two directions. Sometimes the directions are orthogonal, but some rotation it's also possible to be relieved from the images. And if you want to detect the texture, then you will need actually to find out the two directions and also the frequency of the replication in the two direction of this unit called the textile. If you can detect those frequency, then you will detect the textile. If you detect the textile, then you will also find out where this textile is not present, and in this case you will find out the position of the defects. So there are many ways of detecting the texture. I summarize some of them. Actually, what you can do there is to try to find out also in various ways, like the Fourier transform, or we will see the Gabor filters, an analysis of the frequency of the texture in the image. So all those methods are actually at the end trying to discriminate the texture using the same feature, the frequencies. So I will talk about Gabor filters because this is something, it's a wavelet function used nowadays. Actually, the mathematician Gabor defined this function, a complex function, during the 1950s, because it was describing very well the process of modulation, and also they find out that it's also very good representation of the response of the cortical cells of the cells of the visual cortex. So other application of the Gabor function could be in edge detection, and as we will see, in texture detection or classification. So at the end, because the Gabor function has an expression in complex where it's a product, a convolution product between cosinus and a Gaussian envelope in the case of the real part of the function, or a sinus function and the Gaussian envelope in the case of the imaginary part, as you can see here. But we have here two, let's say, two constants that actually are in interest for us. The first one is the frequency, and also the other one will be, as we can see, the orientation, the spatial orientation, because this function could be rotated and positioned in any orientation. So the basic idea using the functions is to try to match them with the texton. Actually, this is the main idea, is using, for instance, the real part of the Gabor function is to try to make a convolution between the image and the function, the Gabor function. If the result is something near 0, then you can say that you have a process called resonance between the texture and the Gabor function. So we do not know any information regarding the texture. We just give to the algorithm an image. So we do not have an information regarding the frequency of the texture. We do not have information regarding the orientation of the texture. We are supposing actually the fact that this texton is replicated in two directions with the 90 degrees between them, the orthogonal direction. So we are actually trying to guess the orientation of the texture and also the frequency of the texture. And guessing means to generate a lot of Gabor filters with different frequencies and different orientations, as you can see in the filter bank that is in the right side of the image. And in this case, I pointed out a filter bank that has 4 frequencies and 8 orientation. So we will have 4 by 8 numbers of filters. So after generating this filter bank, what we will do is to convolve the filters with the image. So this will also be a problem due to the fact that we do not have a knowledge about the position of the texton in the image used to convolve with the filter. So in this case, we will need to cut from the original image a number of subregions. The main reason of this, let's say, cut of subregions is that we are trying to have a better match between the filter and the position of the texton and also the texture in the image. So we will cut a number of regions, n number of regions of certain dimensions, because we will try to speed up a little bit the process, and we will convolve the sub-images with each of the filter banks, and at the end we will compute an average result for each filter, because we will try to guess which filter will match with the texture in the image. So at the end we will have a result of an average result for each filter applied to n subregions. So we will retain all the results, but of course we will try to find out using this kind of cost function, which is a normalized one, which filter will have the highest cost, meaning that which one is the filter that matches, have a better match with the n sub regions that we have cut from the original texture image. And at the end, we will select the one that will give us the highest cost. If we manage to find out which filter is the one that in the convolution process has the highest response in this case, then we find out the filter that will give us the frequency of the texture, but also the orientation of the texture. In this case, this filter at the end will have a better response. A better response in this case means that we will have a 0 response for the convolution, but it will also give us a maximum or a minimum response in the case of the non-texture being present in the image. So we have the filter that better match with the texture, but also it will give us a different response if the texture is not present there. So at the end, like final threshold applied to the response of the filter in the portions where the texture is present or where the non-texture is present will give us a separation into classes of the pixels belonging to the texture detected or the one not belonging to the texture detected. So we made some tests. At the beginning, we were using the benchmark which was publicly available on the internet, the product set, and after that we also acquired the images of texture defects in our lab. But at the end, as you will see, we have applied everything on a system that we have built for Takata Petri production site in Sibiu. We will try to and actually manage to detect different defects like a breakout, like a thick yarn, a mispeak, a dirty yarn, or let's say stains. In this case, you have, and on the left, a textile which is without any defects. On the middle, you have like stains, and in the right side, you have an image of a thick yarn. For the case of airbags, as I will mention, this is something to avoid. You have here an example of a texture which is not, let's say, orthogonally oriented. It has, as I mentioned, a breakout, and you will see the response of several filters, not actually the selected one, which is on the right side bottom. The response of different filters on the texture. So you can see that the filters respond differently based on their orientation and also based on their frequency. So the one that actually discriminate better the texture and the non-texture is the one on the bottom right side. And some other results, breakout and also thick yarn, in this case not on the airbag weft, but on other examples, and also the result of the thresholding and recognition process, pointing out the region where the texture is not recognized as the one that we already discovered before. So we try to implement our knowledges about texture detection on a plant that is producing airbags here in Sibiu. It was quite a challenge for us due to the fact that the threads that you see here using for producing this weft are very, very small, very thin. It's something like 0.25 millimeters in diameter, are done in polyamide. The control of the threads, it's very well done by the producer, and they use some looms for production of the textile of the weft, which are made by Toyota, and are some water jet looms, the highest productivity looms that are in the world. The production of this weft must be very well controlled. The stains are not important, but the thick yarns, the breakthrough, the mispeaks are very important, because if there are some inequalities in the weft, the airbag that will be produced is not a quality one. It will not respond to the functionality. So the basic idea is that using the weft produced by the looms, actually they have like 60 looms working 24 hours a day. It's quite a noise there in the production site, and not only noise but also vibration. They need to stop each month the production in order to make it replace the looms, because they are due to vibrations moving in the site. After the production of the weft, of course, there is another stage that I pointed out. Here they will make a coating with silicone of the weft in order to make it low air, or providing a low air permeability of the weft, and the airbag will be as a balloon, but not a balloon that remains inflated, but it needs to deflate and have a control process of deflation, as the action of the airbag, like life preventing device needs to be preserved. So what we have done is to try to detect the defects being present in the loom. We started making some tests at the beginning with only one camera. We use a professional camera made by Baumer, 5 megapixel black and white camera, gigabit, and also power over Ethernet. And after that, we saw that we will need also a lightning. We use LEDs for lightning. We try to find out the better position in order to get all the information required for detecting the defects. I told you that the diameter of the threads is 0.25 millimeters, so we need a lot of pixels in order to have in the image all the information, the threads being present in the weft, and we managed then to develop the system. The system is based on 6 cameras in order to cover the 2.5 meters length of weft produced by the loom. And of course, the system was made using a touchscreen computer, and also we feed out all the data to a server that was in the production site, in order to be analyzed, not at the position of the loom, but by the quality inspection, quality assurance personnel that are not there in the production site. So at the end, the system looks something like this, and it was made to be portable. The basic idea was not to implement the system on all the looms because the cost of the system was somehow high, but actually they did something smarter than detecting the defects. They tried to change the maintenance schedule of the looms, because the looms need to be maintained in a schedule provided by the Toyota, by the producer of the looms, but they actually find out that they need to change the schedule in order to reduce the number of defects. And they try to find out what are the causes of the defects, because the threads were actually controlled by the producer of the threads. The only unknown and big unknown in the question was the loom. So they make a study using the system. So this is why the system was moved from one loom to the other in order to find out what was the causes of the defects. They also make an analysis, time analysis, or let's say date analysis between the defects and also the mentioned stops or other incidents that were reporting by the operators of the loom. So at the end, they managed to reduce the number of defects by changing the maintenance schedule, and also by finding what were the links in this production chain that were causing the defects. So this is the, let's say, the final use of our system. We also managed to make another control system there at the production site of Takata, because after the production of the weft, in the case where everything is okay, the weft was coated using a silicone material, and after that they cut it and of course sew it to get the final product. But there are using some automated machines that are sewing using a certain pattern. And of course, it is possible that due to the machines or due to the threads that are using for making the seams, if the seams are not done in a continuous way, the airbag won't perform as it will be expected. So you can see here some defects that was used in our studies. In this case, in the left side, you have a miss seam. In the right side, you have a double seam, and also some views of the miss peak of the seam in the lowest part. There it's a double seam, but you can see somewhere in the middle left side some miss peaks of the seam. So if those things are being present in the final product, the airbag won't perform as expected. They can break, they can deflate in a short period of time, so the airbag won't perform as it was expected. So we try to apply some knowledges from the image processing field. It was quite a good environment here because they used different colors for the seams, for the threads of the seams, and of course we had a contrast, a good contrast between the seams and the somehow pink coated weft that we were discussed before, because the silicone that they use for coating is in a pink color. So what we have done, actually, you have some images here. After acquire the images, we are trying to make two segmentation, one based on color in order to recognize the portions of the image where the seam was present, and also then using the half transform and morphological informations to find out if the seam was linear or a circular or a partial circular one. And based also on the shape of the seam, because you need to know some morphological information regarding the shape of the seamed assembly, then you could find out if something was wrong there or not. So as you can see, we have some partial images of the steps of processing, the defects that I pointed out, and at the end, the results of the processing steps. We managed to find out where the thread was broken and the seam was loose. And of course, if due to some other mechanical properties the seam was doubled, or if it's not doubled, they have a mispeak in the seam. So as I said, not only the defects present in the texture plays a role, but also some other defects that could arrive during the production process. In this case, seams or stitches or cutting can also be emphasized using this kind of automatic control based on image processing and, of course, computer vision. During the times, I managed also to make some other applications for this quality control in the texture manufacturing. One of them is regarding the seam puckering. So puckering means that when you are trying to assemble two parts of the using the seaming process, if you cannot manage to flatten the textile, then or if the sewing machine is not controlled and it's not tuned perfectly, then you will get this kind of defect called puckering, which is actually visual aspect defect, because the final product will not be pleasant to the person that is wearing the product. So you need to avoid this kind of results. Actually, the evaluation of puckering can be made by machine vision, and I'm not actually talking for the cases where the seaming is done by humans, because they can control the process, but if the seam is done by an automatically process. And another aspect that could also be mentioned here in the case of quality control is the assessment of peeling. So peeling is something that we can, all of us can see or mention because we have knitted fabrics and wool, let's say wool knitted fabrics or cotton knitted fabrics. In the case of cotton, peeling is not appearing so oftenly, but in the case of wool, due to the wearing of the product and due to the mechanical friction of the product, the peeling is a result, and we actually do not want to have this kind of result because it's something that we visually do not like. So the producer are trying to avoid it by making all kind of threads or a combination of materials in producing the threads, and they try to assess it using some special evaluation in the production site. So at the end, the assessment can be done by humans using five grading assessment levels, but it can also be made by computer vision, making some texture and detection, and also then by processing the results to see if you have a certain grade of peeling after a certain number of, let's say, mechanical friction of the material. So because this industry is a traditional one, but also a very dynamic one, ready-made garments and textile goods are all over, not only for clothes, but also for the seats of the car, the airbags, and many other areas. There is a constant need for quality, and in order to have a better quality, you need to control very well the production cycle, and starting, of course, the designing. As I said, the evaluation or assessment of peeling is made in this step of design of the product in order to have or choose threads that can give you less peeling, for instance, in the manufacturing, and also then in the maintenance stages of the production cycle, as I pointed out by the application that we have done before. So all the elements being present in the production steps need to be controlled. Of course, not only the incoming products or ready-made products, but also the steps of sewing, wearing, and the maintenance of the equipment that are used for the production is needs to be done. The human factor, it's here the weakest part. Computer vision could replace the human operator and make the operation of, let's say, classification, in this case of products with defects or non-defects in various in a higher speed and in various ways. So I try to point it out the need for automatic controls. I also try to point it out that we can control the product, but we can also control the machines used to make the product, and we can improve by controlling the both elements the way the quality of the product will be presented. So this was my presentation for the assessment of the products in the case of the textile industry. If you have questions.
So if you have questions, do feel free to expand the GoToMeeting panel and put them into the chat. Now, first of all, Ermus, very interesting presentation. Thank you very much. I have two questions. If you could expand a bit, first of all, at the very beginning, you mentioned the cost function, which helps get a better match. Could you tell a little bit more what is the cost function?
Yes, actually, the idea is that, as I told you, we are trying to find out what is the dimension of the texton, or in this case, something indirectly, the frequency of the texture. And we do not have any knowledge about the position of the texture in the image. And in this case, we do not know the position of the texture in the subregions that we are trying to obtain by dividing the image in n subregions. And if I may turn here, you see we have a shape for the Gabor function, and actually you can see here a three-dimension representation of the Gabor function. For instance, the gray level, the medium gray level means 0 level, because we have positive and negative values, and white ones means positive values and black ones means negative values. So we are making a convolution between one of the filters and the sub-image that we have cut from the original texture image. And we don't know the frequency, we don't know the orientation, but also we don't know the position of the texture correlated with the position of the filter. So this is why here we are computing an average result, and afterwards we are trying to guess which is the filter that is better matching with the sub-regions or the sub-images that we have extracted from the texture image, the initial big texture image that we are trying to detect or extract the features from that texture. So this is why we end up with this kind of normalized cost function, because we are trying to in this case maximize the cost.
Thank you very much. And the second, you mentioned something called products as a benchmark for the images. Could you tell me what is it?
Okay, so at the beginning we didn't have texture images, and of course we because every time you are making up with an algorithm, you are trying to test it, and you need to test it on a benchmark. And at the time, now I find out that there are several texture benchmarks available, freely available on the internet. But at the beginning, the product set was the benchmark that was available, and they had a lot of textures with different dimensions, orientations, and so on. So we use it even if they didn't have like defects. We simulated the defects on the test set. It's called products because it was the name of the one that submitted freely on the internet. So we use this set to validate our wavelet algorithm in order to find out if it works. And after that, we also use real life images that we have acquired with our cameras in our Vision Lab.
Thank you very much. Do you have any more questions? So if so, it is a good time for the audience to put them into the chat. I don't see any more coming. So one more time, thank you very much for a great presentation.
Thank you.
To all of you, have a great day. And I would like to invite you to our next DigiFoF webinars. Bye-bye. See you. Take care.
Bye-bye. Thank you very much. Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye-bye.